pure bending. We're basically looking at beams. Remember, there's a couple requirements of the problem. One is that, well, if we set x this way, y that way, and then z out of the board, our problems are subject to a couple restrictions. Remember what any of those happen to be? In terms of both the bending load, the moment, and in terms of the cross-sectional shape itself, which we're now getting to the point where we can size that, get the right size of cross-section, the right shape even, to help us get a beam that can withstand the loads. Remember what the, Chris?
Symmetric.
Symmetric, not symmetric about the x-axis, symmetric about the y-axis. So if we look at the end here, looking down the x-axis, we'll see the z and the x like that. Our cross-section must be symmetric about the y-axis. It doesn't really matter what it is. We can do all kinds of shapes as long as it's symmetric about the y-axis. That's our only requirement at the moment in terms of the, well, it'd be nice if it actually looks symmetric, wouldn't it? No, there we go. And then the only other part of the concern with that is, if you remember, we need to find two things with this cross-section now. We need to find what we call the neutral axis, and we'll review in a second why we need that, but it turns out it goes through the area centroid anyway, so it's just a matter of finding the centroid of that area. And then from there, then we can find the bending, because the stress as a function of y, if you remember, was whatever moment is being imposed. And there's another one of our restrictions. The moments must be in the z direction. Remember, using the right-hand rule, that gives us a moment that's purely in the z direction. And then we found that the stress was a function of that moment, the position across the cross-section, and then the moment of inertia, area moment of inertia. And so if we look at some cross-section or some profile, some stress profile, we saw that for this kind of bending, the top is, of course, in compression, the bottom is in tension, and it was linear between the two. And it was zero at this place that we call the neutral axis, which goes through the area centroid. So if you remember, that's pretty much where we left things off. Chris, you okay? You look like I might have put something up there wrong. Technically, there's a minus sign here because positive y was up, but that gave us a compression for this positive moment. Remember, this was our positive, our convention for positive moment. So if we had positive moment and positive y, we needed the minus sign to tell us that that was in compression above the axis and tension below the axis. But tradition has it that the minus sign is often just left off because it's so obvious just from inspection of the problem whether it's compression or tension. You just look at it and you're going to know what's going on with that piece. So let's do a quick reminder of how we find this centroidal axis, because that's where our stresses are zero, and then we know they're linear in between, and that their maximum where we're at the maximum distance from that neutral axis. And that was the symbol that we gave the letter C. For some reason they picked that to represent the maximum distance from the neutral axis. And remember, this neutral axis might not be right in the middle, so the greater distance might be below the neutral axis rather than above. It depends on where the neutral axis falls. Depends upon what the cross-section looks like. So we'll remind ourselves how to find that neutral axis, because we're going to need that with what we're doing next. Oh, there is one other thing. If you remember, this stress distribution actually came from the strain distribution, which we established first. However, because our material is homogeneous and isentropic, which means it's the same material throughout, same densities, same material properties, everything. The stress distribution led to the strain distribution, sorry, other way around. Stress distribution, which is what we found first to be linear, led to the stress distribution, but that's also linear because they're related by a constant. If you remember, they're related by Young's modulus. And since that's a constant, then if the strain distribution is linear, so is the stress distribution. We're going to need that in a second when we get to that. So we've got a quick problem here. I want to find the neutral axis for a cross-section made up, just exactly the type of thing you might build out of 3 boards if you were looking to build some kind of support beam of some kind. And all these measurements in millimeters, and we want to use that to find the neutral axis, which just by inspection we figure is going to be someplace around there, give or take a little bit. So when you get an answer for the neutral, where the neutral axis should be, you can look at it and check and see if that's even reasonable for what you might expect. So just to aid things a little bit, I'm going to label some of these dimensions. We'll label this. This will be piece 1, and that is of width B1 and height H1. I'm going to go through this very quickly because this is just review, just a warm up from spring break. And I'll call this distance H2 and this distance on the second one B2. And you'll see why in a second, why I did it that way as a refresher for that too. So if you remember, what we need to do is find the position of the neutral axis, which I believe we call a y-bar, which we find by looking at each of the individual pieces and calculating the product yi, which is the location of its own centroid, the individual pieces. I only have 2 on here. And then sum that over the total area, total cross-sectional area, and that'll locate the y-bar for us. We only need one other little piece. We have to pick some arbitrary reference line. So I'll choose it from the top, but you can choose it from anywhere you want, anywhere that's convenient. If you'd like to do it along the bottom of this upper plank, no trouble. If you want to do it from the bottom of the beam, no trouble. All you're trying to do is locate the position of the neutral axis. And once we find that, it's fixed to the cross section. We don't need that reference line anymore. We just need the reference line to get going a little bit. as we plan through things. All right, so I think it works well if you make yourself a little table, just less chance of making some kind of error. So we have these two parts here. For each of them, we're going to need to locate the centroid. For each of them, we need the area, and then for each of them, we need the product of those two. So it works nicely if you do it in the table. The location of the centroid of the first piece, of course, is right in its own middle, which is 1/2 H1. Remember, that's locating the centroid of piece 1 with respect to our reference line. Piece 2 is also right in the middle. So that's a distance from our reference line of H1 plus 1/2 B2. And you can get H1 and B2 from the reference or from the drawing itself. I'm just trying to lay out a skeleton solution to this because it's just review, a reminder for us. So the area A1 is B1H1. Remember, B1 is not 200. That's the inside dimension of this channel beam that you've made out of some planks. B1 is going to be 20 millimeters plus another 20 on each side to get to the outside. So be careful of those kind of things. It's excuse me, really easy to slip up with that. And then, of course, the area of piece 2 is B2H2. However, there's 2 of them. So we can just double it, or you can call it number 3 if you want and just add it on separately that way. It doesn't matter, it all comes out to be the same anyway. And then we can multiply those, and I'll actually put those values in so you can double check them later. We'll call, let's see, this comes out to be 75,000 millimeters cubed, and this one comes out to be 600,000. And so we total that up, 675. We also total up the area because we need to divide that 675 by the area, and the area is 12,000. So we're all done. We got all the pieces we need. Remember to watch your units. Be careful with it. Don't rush through this thing. Notice this is just a personal habit, but I put a little space where typically in America we put commas. In lots of European countries, they see commas as decimals, so it's very hazardous for us to use commas if somebody that we might be working with in Europe would see that as a decimal and have a completely different number for their design. So if you just leave a space, you get the benefit of that grouping by 3s that keeps the mistakes down, but there's not a misinterpretation of what a comma or a decimal might mean. All right, so with that, we get, we divide those two, get y bar 56.25 millimeters when we divide those two. And that's right about where we'd expect. So we now know that y bar is 56.25. We're down that far from the top, our arbitrary reference. That fixes the neutral axis right on our cross section, and we don't need to worry about where the reference line was anymore from that, 'cause now we know where the neutral axis is. One last thing we need to find then is we need to find the area moment of inertia of that cross section with respect to the neutral axis. to do that, we sum up the individual moments of inertia with respect to their own centroid, and then we apply the parallel axis theorem because the axis we're concerned with, the neutral axis, is probably not going through the centroid of any of the pieces. So again, a table might help as you do that. We've got two pieces here. We need to find out their centroidal moment of inertia. That's in the front cover of your book. If you just open that there, you'll find the shapes for the different regular solids, and certainly rectangles are in there. For these pieces, it's 1/12 d1 h1 cubed. And then you've got to be careful with the other one because as it's drawn in the book, piece 2 is 90 degrees from the picture in the book if you look at it in the x-axis, or if you just take it in the y-axis direction. But that becomes h2 b2 cubed. Just because the orientation of those rectangles are 90 degrees to each other. For each one of those, we need to figure out what d is, because that's part of the parallel axis theorem, the AD squared. So in this case, I'll just write down the numbers. You can double check where they get them. Remember, this is the distance from the neutral axis that we just placed to the centroid of each piece. So that distance there is d1. This distance here is d2. As measured from the neutral axis. We don't use the reference line anymore, we just use the neutral axis. By coincidence, they happen to be the same. In this case, it's not usual because remember it had to do with all the widths and the lengths and all kinds of things from that. It just happens to be the same to the two of them. This will have units of, oops, to the fourth, not to the third, millimeters to the fourth. Now we can add I plus A, which we already have, plus D squared to now get the moment of inertia of each piece with respect to the neutral axis. Then we just add those two up to get the moment of inertia for the entire cross section. So these numbers turn out to be, because we're in millimeters, these turn out to be pretty big. 11.8 times 10 to the 6th. This is millimeters to the 4th. And then 2 times, because there's two solids, two portions on either side, 11.4 times 10 to the 6th. You'll have to double check it. My recollection is that maybe this first 6 should be a 7, but I have a 6 written down. So double check that number. Then we'll get it right when we take this again next year. And those add up to be 34.6 times 10 to the 6th millimeters to the 4th. And now that gives us the I that goes into there. The Y is measured from the neutral axis. And if we had some given load, then we could figure out the stress at any point across the solid. look a little familiar now that we kind of flew through that in sort of a skeletal way? Phil, are you checking whether this is a 6 or a 7 for me?
It's a 6.
I know it is a 6. Okay, I know that one's right. So, yeah, I guess so. If we look at that, that'd be right. Okay, we're going to need that again coming up here. Finding the moment of inertia and the location of the neutral axis for a cross-section of compound shapes. We're going to need that, and we're going to need these two ideas as a reminder for what we step into next. Now, with all that, remember one characteristic of the beams that's held true throughout all of this bending that we've been doing is that the beams are all made of one material. No matter what the shape of all these different pieces are that are put together, they're all the same material. There's certainly the possibility that we might want to do something other than that. If we have a beam in simple bending, like we've looked at before, we know that the top part is in compression, the bottom part is in tension. You also know that wood is very good in compression and terrible in tension. So you might say, well, why don't we make the top part of the beam wood, because it's cheaper, it's easier to work with, it's very attractive in a structural setting, especially a home. It's great in compression. Maybe we'll make the top part wood and the bottom part maybe steel or aluminum or some other material. And the beam could also be lighter that way. So there's several reasons we might want to do this. Any one of those might be worth it to you if you ever become a structural engineer. The trouble is, when we look at the loading then in the piece, remember we first established that the strain, the normal strain in the x direction is linear. Then because those two materials were the same, we also then established that the stress was linear in the same way, because of the constant Young's modulus that related those two. This is only if the beam is homogeneous, meaning the same material throughout, which is not the case if we start looking at a two-material beam. So the trouble comes now that the strain will be indeed linear. That doesn't change. That was only dependent upon the cross-sectional area. This came from the fact that stress and strain are related by Young's modulus. If we have a different Young's modulus for the top than we do for the bottom, we can now expect some kind of stress distribution that may look like this. Wherever the neutral axis is, we know that it's linear through there. Let's see. Here's our second material across there. So we know it's linear through there, but now we have a different material that would have some different type of stress and have its own distribution that would look something like that. This, by the way, this little sketch is assuming that E2 is greater than E1. If it was less than, if E2 is less than E1, then the stress distribution at the top would be greater. However, we can't just calculate that by applying the new, the different Young's modulus, because the trouble is we don't know where the neutral axis is for this distribution. It might not be at the same place it was for the uniform cross-sectional beam. So we need to do something to establish where this is. Then, when we've got that, we can apply this linear distribution depending upon what E is on either side. These are called composite beams because they're made of two different materials. We're assuming that the whatever is holding the two materials together is perfect and will not fail itself. We'll look into that in a little bit, a couple weeks. So whatever is bonding these two together is, as most things are in my classes, perfect. So we've got to figure out some way now to handle this so that we can figure out what the stress distribution is. The thing is, we just don't know where the neutral axis is for that distribution because this is a completely different beam. So here's what we're going to do. For a design of composite, remember, prismatic beams. Prismatic is that deal where it's symmetric about the y-axis. So we have this beam. We'll just start with this simple shape like this one, where at some location, not necessarily right in the middle, that's just too convenient, I'll put in, we'll change the beam into made of two different materials. The top one with some Young's modulus and the bottom one with some Young's modulus. Because remember, that's what determines what the stress is. The strain is still linear. The stress is no longer quite linear. Well, it's linear, but it's disjointedly linear, I guess, if you will. So here's what we're going to do. Everything we've done so far has been for beams of homogeneous material, the same material throughout. So what we're going to do is we're going to take that composite beam, turn it back into a beam of homogeneous material, and then analyze it like we would have before. So we've got this beam here. Let's see, we'll call it of width B, and we'll keep that on the top. Then we'll take out the material at the bottom. It's one or the other that are giving us trouble. I'll assume in this case that the Young's modulus for the lower part is greater. So I'm going to take out that stiffer material and replace it with the original material that's not as stiff. Because it's not as stiff, I'm going to need a lot more of it. So I'm going to put in a whole bunch more of this material, and now it's entirely homogeneous and essentially equivalent to the beam we're trying to design of two different materials. So now this beam is entirely of the material with stiffness E1. That we can analyze. That we've been doing for a week or two now, depending on what you did over break, which I'm sure was homework. Trouble is, how big do we make this? How much wider must this be than it was originally so that we have enough softer material in here now to replace the stiffer material we took out? Turns out that it's a factor that we call n times wider, where n is simply the ratio of those two. So if the bottom one's twice as stiff, we take it out, use the less stiff material, and use twice as much of it to get the equivalent ability to withstand the stress. You can, if you'd rather, go the other way. Leave the stiff material in, replace the softer material with the stiffer material, and no trouble, you just use less of it. So this would be then B over N. Actually, I don't want to hatch that in pink because that was my 1 material, so this is my 2 material. You can do it either way. It doesn't matter, it's going to come out with the same results, and you can double check that if you want. Now we take this new cross section. I don't want to do 2 at once, so I'll erase that one. We take this new cross section and we now find out where the neutral axis is for this cross section. From that neutral axis, we now find out the moment of inertia. And then once we've done that, then we can find what the stress is as a distribution, as a function of y position across the beam with respect to the neutral axis. Which is a problem we started the week before break, and we just reviewed again today.
The geometry of your new and large size doesn't matter, or you just want to do it in a way that's easy for you to manipulate?
No, it does matter because it depends upon what the original shape was. It's still fundamentally rectangular. And it depends upon what the materials were, because that tells us how wide the new part is. Remember, we've taken out this stiff material here on the bottom so that the entire beam is made of the softer material, so we needed a whole bunch more of that softer material on the bottom to represent the stiffer material for which we're designing now. We'll do a problem. We'll step through it. That sometimes is an easier way to do it. So we'll actually go through this. All right, so let's imagine we have a beam that's got an aluminum plate on the top and wood on the bottom. Now, depending on what load it carries, that may or may not make a lot of sense, but it might be aesthetically pleasing to have this wood on the bottom. So we've got the quality of the aluminum across the top, but the aesthetic view, the beauty of wood. If you were a structural designer for a great Adirondack camp, your customers are not going to be real happy if the beams are aluminum. They're going to be a lot happier if the beams are wood. So we'll design for that kind of wood. I mean, that kind of beam. So let's see. The Young's modulus for wood is 10,200 KSI. For the aluminum, it's 1700. So significantly, wait, I got those wrong. That doesn't make any sense. Sorry, reversed. 10,200 for the aluminum, 1,700 for the wood. That makes more sense. And the dimensions here. The aluminum is 1/4 inch. The wood is 8 inches. The width, 3 inches. Okay, so that's our composite beam. All right, so for pure cross section, looks like that. Wood on the bottom, aluminum on the top. We're going to take out one or the other and replace it with an appropriate amount of material. We can take out the aluminum, replace it with wood, and we're going to need a whole bunch more of that wood. Or we can take out the wood, replace it with aluminum, we won't need very much of that because the aluminum is so much stiffer. Doesn't matter which, so I'll take out the aluminum and replace it with an appropriate width of wood. So now this cross section is all wood. Now remember, this isn't the final design. This isn't going to be what it looks like. But this is what we need to do to make it equivalent for our design purposes. So the bottom is the wood. We left that in. Oh, it's not quite to scale. It was supposed to be that wide. Maybe I'll redraw that just so it's not confusing. There we go. So that remains the same. We replace the top with an equivalent piece of wood that's wide enough to withstand the same stress that the aluminum would. How much wider must this be then? It's going to be n times 3 inches, where n is the ratio of these two. You can do it either way. It doesn't matter. Just make sure that what you're doing makes sense in the end. This comes out to be 6. So the width up here will be 18 inches. That we assume to be an equivalent beam. It's not a very attractive one. It's not what you're going to install for your customer, but it is one for which we can figure out where the neutral axis is. We can figure out what the moment of inertia with respect to that neutral axis is, and we can figure out what the stress distribution is. All right, so we need to figure out where the neutral axis is. I'll again pick a reference line from the top from where I'll calculate everything. Now all the calculations are for this new cross section. So first thing we need to do is figure out where the neutral axis is. then once we've established where that is, we know it's going to be somewhere up near the top here because of the extra area up at the top. So let me keep my numbers straight. I'll call that piece 1, this piece 2, and we can do like we have before. Figure out where Y is, what the area is, and then the product of the 2, and sum the area and sum that product. Okay, for piece 1, its centroid, with respect to our arbitrary reference line, is halfway across the 1/4 inch thickness, so it's 1/8 of an inch, 0.125, where that's in inches. Its area is what, 18 by 1/4, which is 5625, I think. Is that right, John? No, I looked at the wrong one. 4.5. It's the product that's 5625. And that's inches squared there, inches cubed there. All right, piece 2, its centroid's right dead center, which is 4 inches down through the piece, but we're already 1/4 of an inch down, so this is 4.25. Its area is the 8 by 3, that's 24. So we can add up the area, 28.5. And Y bar, or Y times A for that individual piece is 102. So we know this to be then 102.5625. And the neutral axis then is those two things divided. We figure it's got to be 2 or 3 inches down here. That looks like what it's going to be. Actually, it turns out to be 3.59. Doesn't hurt to carry a little bit extra significant figures. Phil, you'll love these problems. Carry through some of the significant figures until the end. So that's Y bar. We know to be just under 3.6 inches from our arbitrary reference line. Now what? Now we figure out the moment of inertia with respect to that arbitrary reference line. Which is the sum of the individual ones with respect to their own centroids plus the parallel axis theorem. All right, so for each of the individual pieces, we need to find its centroidal moment of inertia, its moment of inertia with respect to its own centroid. Then, since we're using the parallel axis theorem, we need to then move it over a little bit, and then that's the last piece we sum up there. All right, let's see if I have all those numbers. They're all rectangular, so it's the 1/12 BH cubed. Just make sure the orientation's right. This first one is 0.02344, and that's inches to the fourth. You can check these. We're going through these kind of quick because these are just geometric calculations that you can make. This one comes out to be 128. D, remember that's the location of the centroid of the individual piece with respect to the neutral axis that we've now placed. And that is, for this first one, 3.4734. Remember, that's down the 3.599, back up a quarter of an inch. Or a quarter of an inch taken off.
I think it's 3
What?
points.
Did you say
Three, I said, yeah. I just like fours. Too bad they don't do that on my paycheck. 3.47. You guys are awake after break. And the second one is 0.6513. Now, it doesn't matter if D is above or below the neutral axis. We don't care about a minus sign being on that, because in the end, we use D squared anyway, so it doesn't matter whether we're above or below. One of the few times we don't have to worry in the least about minus signs. Okay, so AD squared, A we've already got from the first table, D squared. This becomes 51.3. By the way, that's inches. This is still inches to the fourth. So 51.3 on that last one. 10.2. Oh wait, sorry, that's just A D squared, not I plus AD squared. Oh, but it doesn't change much. 51.32 for that one. And 138.2. And you can check all these. For testing on this kind of problem, it'll probably be a take-home one, because there's so many places you can make little tiny mistakes that it's virtually guaranteed in the test, the time of a test and the pressure of a test, you're just going to make some little mistake that really doesn't indicate you're not getting the idea anyway. So I'll give you a take-home, see if I can ruin your weekend. 189.5, that's the moment of inertia with respect to the neutral axis. Now, before we finish this problem, because that was the easy part. You could have done that the week before break. What we need to do now is calculate this stress distribution in these pieces. So let me erase this part. We'll apply some load to this and then figure out what the stress distribution is. Remember, the strain distribution remains linear, because that only had to do with the cross-sectional shape. Didn't have anything to do with the material. The stress that comes from that has to do with the material. So let's imagine a moment was applied of 6,000 pound-inches in our usual sense.
Or 60,000?
60,000. Yeah, 60,000. And then from that, then we can figure out what the stress distribution is. So here's our beam. Now we've got all the things we need, because remember the stress is a factor of that moment of inertia. But here's the little piece we need to be careful with. We now know the neutral axis to be right about here somewhere. So the strain distribution is linear, just like it was before. It's just now we know where the neutral axis is, and it's not where we would have placed it with just that simple rectangular beam. So the strain remains the same, still linear, still zero at the neutral axis. It's just now we know where the neutral axis is of our equivalent beam. The stress distribution is a little bit different. Neutral axis across here. The stress distribution, well, the bottom is just the same. Remember, we had wood on the bottom and we made the beam entirely of wood, so that's still going to be the same. That's still going to be just like it would have been if we calculated it before. With those very same numbers that we've got there. So we've got a applied moment of 60,000 pounds inch. C now, remember, is for the wood is all the way down to the bottom from the neutral axis. That number comes out to be, where do I have that? Oh, I don't have it actually written out. Here, John, you do it for me. 8 1/4, because that's the entire beam minus that neutral axis 3.599. Then we had 8.25 minus 3.599.
4.651.
Okay, 4.651. And that's inches. That's how far the farthest away piece of wood is from the neutral axis, and divided by the 189.5 inches to the fourth, and we're left with good units, PSI. And it's 1473 PSI in the wood. And that we know from the problem is compression. I know, I guess I didn't put any direction on the moment, so evidently it's being bent the opposite way as usual. All right, so that now gives us the distribution of the stress in the wood. I don't know, that's not compression. I don't know where that came from. Now, the distribution in the aluminum is a little bit different. We do the same basic calculation. Now we're doing the aluminum. we're looking for the maximum. We know it's linear in between. It's the same moment times C for the aluminum, which is that little bit left over. In fact, that is Y bar, what we already figured for Y bar, over I. But we need to multiply that by that factor N that we had. Because if we don't, we'll just get the same distribution we had there, but the aluminum can withstand a much greater strain than can the wood. So we have to put back into the calculation that that actually was aluminum. So N was 6, M is 60,000. We already know what the units are going to be. We're okay with that. Y bar is all that goes in here. 3.599. And I is the 189.5. And we already know what the units are going to work out to because N is unitless. And we get 6837 PSI, which is 6 times greater than it would have been if that was just a wood piece there. And that's now linear all the way back to the neutral axis. So that's like that. A little hard to draw. Much greater compression ability of the aluminum, which is part of the reason it may have been in there. Might have been that for that load, the wood would not have been sufficiently strong. So you put in an aluminum plate across the top that absorbs a lot greater stress, and then put the wood on the rest on the bottom for perhaps aesthetic purposes or for weight purposes. And we've got the whole picture there now. All right, it's this little step there that students often forget. You have to apply that factor of N. And remember, you can do this the other way. If you want N to be the lighter one over the stiffer one, you can do that too. You're going to find that you still all come out with the same calculation. So you can go either way. You just have to be consistent with it. All right. Any questions before you do your own? All right. Let's see. Should I give you a hard one or an easy one? Actually, they're about the same. Maybe we can get 2 in here real quick. So let's start with a fairly straightforward one, only it's a bit different than what we just had. All right, we've got a beam here, oops, not to scale as usual, that's made up of 2 materials. On the outside is brass. And the inside is steel. Again, might do that for aesthetic purposes. Brass is a lot of times a much more attractive metal than steel might be. So the brass is 0.4 inches thick, the steel 0.75. Symmetric, the other brass piece is the same, and all of 3 inches high. All right. The load is 40 kip inches. A kapinch. And the Young's modulus 29.6. 29 times 10 to the 6th psi for the steel, and for the brass, 15 times 10 to the 6th. All right. Find the stress, the maximum stress in either. Now, it's not a calculation we can do straight away because we can only analyze a beam of uniform cross, homogeneous material. So we have to take this one and replace it with an equivalent beam, entirely new cross section. And figure out the moment of inertia from that. We need the moment of inertia to figure out what the stress is.